Hello, welcome to Tungal online classes. Now in this session we will see the extent part of induced EMF and the eddy current. In the lecture number 2 we have seen that the induced EMF and the Lenz law. Wherever magnetic flux linked with the called changes and EMF induced in it, that phenomena we are calling electromagnetic induction, and whatever induced EMF that opposes the change produces it. Due to change in magnetic flux, induced EMF produced, the produced induced EMF opposes the change in magnetic flux. That was the Lenz law. And already we have seen that in a uniform magnetic field, if a conductor moving, so in conductor moving in magnetic field with velocity v, their EMF can induce. Now in this session we will see the extent part of induced EMF and the eddy current. In detail we will see. The first concept is induced EMF by conductor rotating in uniform magnetic field or non-uniform magnetic field. This concept we will see. See here in the last class what we have seen, just a conductor moving in uniform magnetic field with velocity v, how EMF induced, right, and how the current induced, that already we have seen. Now in this session we will see, let us take uniform magnetic field, that uniform magnetic field perpendicular into the plane. This is the uniform magnetic field lines. This is uniform magnetic field lines. This uniform magnetic field lines, uniform and perpendicular into the plane. How it is? This magnetic field is uniform. Let us take this value, what value? I can take this magnetic field value is B. Now in this magnetic field, I want to take conductor of length L. How to take? Say it. Simply I will take this nothing but one conductor. This conductor I can take length L I will take. This is conductor. This conductor how much length available? L length available. We know that wherever magnetic flux linked with the called changes and EMF produce. How EMF produce? In this uniform magnetic field, with this conductor moving in circular path. Let us take this conductor moving in circular path. When conductor moving in circular path, magnetic field lines at every point changes because area of the loop changes. So that EMF induces. Look at here. How it is? Let us take this nothing but point O. From this fixed point O, I want to rotate this conductor in circular path. Shall I take this? This conductor moving in circular path. Like this. When conductor moving in circular path, at every point magnetic field lines so with the conductor changes, so that in this conductor EMF can induce. Let us take how the EMF can induce and how to take the direction of induced EMF, how to take the rotation of the conductor, and in what way EMF can induce, that we will see. See here. Let us take this conductor of length L moving in this uniform magnetic field lines. In this uniform magnetic field lines I will rotate. Let us take when conductor moves from this point. Let us take conductor moves from point P to point Q. How it is? See here. Shall I take this conductor moving from point P to point Q? Like this is nothing but point Q. When conductor moving from point P to point Q, it creates an angle theta. How much it create? It create an angle theta. Are you following? See here how it is. When conductor moves from point P to point Q, as it moves from P to Q, it creates an angle theta. Then let us take here. As conductor moves from point P to point Q, how much angle has created? See here from the geometry, what I can take? Angle is equal to what? Theta is equal to length of the arc divided by length or radius you can call. In this case I can take length is here. Right. Then how much arc is covered? PQ is equal to what value? That is L into theta. But as conductor moves from point P to point Q, it creates an area. What area? It creates an area OPQ. So OPQ looks like a triangle. OPQ looks like a triangle. Then we know the area of the triangle. How the area of the triangle looks like? Which one is the triangle here? So triangle OAP looks like. OPQ looks like. In this triangle, shall I take area? Area is equal to half base into height. Base mean what? Base is equal to what value? base is equal to PQ, height is equal to what value? OP, half base into height, base into height, height is equal to what value? OP, right? Then what is area of the loop? Area of the loop is equal to half PQ. What is PQ? PQ is equal to L into theta, right? OP is equal to what value? Length L. Then how much area covered? Area is equal to how much? Half L square into theta. I can call this equation number 2. Simply I can call this equation number 1. I mean, when conductor moves in circular path, I want to take any 2 points such that I take the point P and point Q. When conductor moving, this much area covered. But wherever magnetic flux linked with the call changes, what is produced? EMF produced. How the EMF is possible? Initially, what we know the flux value? Look at me. How to write the flux? Flux is equal to scalar product of magnetic field and area vector. Right. Whenever this magnetic flux changes, how this magnetic flux changes? Magnetic flux changes due to rotation of the coil. This is nothing but conductor. When this conductor moving in magnetic field, at every point area will be changes. At every point area changes. Whenever area change, what will change? Magnetic flux changes. According to Faraday's second law, wherever magnetic flux linked with the coil changes and EMF produces. See here. According to Faraday's second law, simply you can call magnitude of induced EMF directly proportional to rate of change of magnetic flux. Rate of change of magnetic flux. But we know this value flux. Then what about induced EMF? Induced EMF E is equal to d phi by dt into phi. Phi is equal to B into A. When conductor moving in magnetic field, what will change? Only area will change, not magnetic field will change, because this magnetic field is uniform now. Then from equation 2, what about this value? Shall I call this equation number 3? Equation number 3. Now look at it here. So E is equal to d by dt, keep it up same. D by dt keep it up same. B also keep it up same. What is area? Area of this value. How much area? So half L square into theta. Then what is the induced EMF? Induced EMF is equal to how much? This is nothing but B L square by 2 are constant value. What is remaining? Remaining nothing but d theta divided by dt. As conductor rotates in uniform magnetic field, this angle at every point changes. I mean, orientation of the coil takes place here. Orientation means change in angle takes place. Due to change in angle, area also changes at every point. So, rate of change of angular displacement. This is change in angular displacement. You can call change in time. Change in angular displacement by change in time. What I can call? So, this I can call angular velocity. Then, how much EMF induced? BL square by 2 into how much? Omega. This much EMF induced. When conductor moving in magnetic field by this much angular velocity, how much angular velocity? Omega is the angular velocity. When conductor moving in magnetic field, this much EMF can induce. This is extent part of induced EMF. So just copy it. We will move for the one more concept. Concept is eddy current. In detail, we will see what is meaning of the eddy current, what are their applications, and how to minimize. See here. So, shall I remove this? Look at it. Now, concept is eddy currents. Eddy currents. This concept is only on the basis of Faraday's second law. How this concept arises? In detail, I try to explain this concept. This concept is little bit complicated and it has lot of applications. Meaning of the eddy current. See here. Let us take a coil and a magnet. By taking a coil and magnet, we will understand what is meaning of the eddy current. See here, what we know first concept? Wherever magnetic flux linked with the coil changes, an EMF produced in the conductor. Right? If conductor is closed, there EMF produce, and if conductor is closed, both EMF and current also produce. But if conductor is open, I mean it is not a loop, there only EMF can produce, right? How circulating current can produce? By changing the magnetic flux. That concept we'll see. Look at it. To understand the concept of eddy current, simply again we will go for a bar magnet and coil. See here. You can take, this is nothing but bar magnet. I can take this is north pole, this is south pole. Right. Then again I will take a coil. Shall I take this is the coil? This coil contains many circular turns. Many circular turns I will take. Right. So either you can take galvanometer or no matter. So this coil contains many circular turns. Out of number of circular turns, just only I will take one turn. There, how the EMF can produce. Look at it. So out of this number of turns, shall I take only one turn? Again, shall I take this is a magnet. This is magnet. This is north pole. Right. Then from this number of turns, just I will take only the one circular turn. One circular turn. By taking one circular turn, how the current can produce? How eddy current can produce? What is meaning of eddy current here? Look at it. We know that magnetic field lines of this bar magnet, how they can go? These are the magnetic field lines of a bar magnet. Right. This is south pole. How magnetic field lines can go? These are the magnetic field lines of a given bar magnet. Magnetic field lines of this given bar magnet. Direction must be like this. For south pole, direction, and for north pole, this direction. This is the direction of magnetic field lines of a bar magnet. Whenever this magnet is moving towards the coil, more number of magnetic field lines can pass. For example, how it is? Let us take this bar magnet moving towards the coil. I mean north pole of the magnet moving towards the coil. Wherever north pole of the magnet moving towards the coil, more number of magnetic field lines can pass. More number of magnetic field lines can pass. Wherever magnetic field lines can pass in this conductor, in this coil, EMF can induce. How the EMF can induce? According to Lenz law, whenever bar magnet is north pole is moving towards the coil, the current can flow in anti-clockwise direction. Already you know this. Current can flow in anti-clockwise direction. Question is, how the current can produce here? We know that in this coil it contains so many number of free electrons. See here. Whenever magnetic field lines can pass through conductor, each free electrons in an conductor on in a circular loop, they experience magnetic force. Wherever they experience magnetic force, they can move in a circular path. Shall I take actually, if an observer standing here, this is nothing but shape of the coil, right around. Shall I take here one more way? Look at here. Again, this is nothing but circular turn. Simply I can take like this equation. So in this circular coil, how the magnetic field lines can pass? These are the magnetic field lines they can pass through given conductor in this way. Are you following me? In this way magnetic field lines can pass. Look at me. This is the way magnetic field lines can pass. When magnetic field lines can pass on this coil, so many free electrons available. Those free electrons experience magnetic force. As a result, all free electrons moving perpendicular to magnetic field. If this is nothing but magnetic field, how the electrons can move? All the electrons, for example, this is one electron can move like this. Or how the electron can move at this point? At this point, electron can move like this way. At this point, electron can move like this way. Like this way, electron can move. In this way, electrons can move like this. Like this equation, number of electrons are moving. When electrons are moving in one direction, what is the direction of current? Direction of current is opposite to direction of motion of the electron. I mean, if electrons are moving in clockwise direction, how the current can produce? How the current can produce? Current can produce in anti-clockwise direction. Current can produce in anti-clockwise direction. This is nothing but direction of current in an conductor. Again, the produced current, this produced current opposes the change produces it. Opposes means whatever this conductor, whatever this current produces, the produced current again it is act as a magnetic dipole to that coil. Due to magnetic dipole, again it opposes the change in magnetic flux. How it is? Look at here how the electrons are moving. Electrons are moving in clockwise direction like this, right? Electrons are moving like this. Wherever electrons are moving like this, how the current can produce? Current can produce in anti-clockwise direction like this situation. Simply I will take, so one more I can take. Look at here. See here, this is nothing but coil I can take. Very simple, this is a coil. So in this coil, this much magnetic field lines can changes. Wherever magnetic field lines can changes towards the coil, how the electron can experience magnetic force? Electron experience magnetic force in clockwise direction, like this. If electrons moving in clockwise direction, circular path, how the current can produce? Now current can produce in anti-clockwise direction, like this way current can produce. Then how this current looks like? This current looks like a circular loop, or looks like a Foucault, or looks like a water it is. Look at it. Again, this produced current, whatever this produced current opposes a change in magnetic flux according to Lenz's law. When current flows in anti-clockwise direction, so this acts as a north pole. I can take this nothing but north pole. This acts as a north pole. What about this act as a south pole? So magnetic field lines can coming from north pole. This is the north pole. This is the north pole. North by north. In this situation, how it becomes? It becomes like this. This is north. This is south. North and north repel each other. That according to Lenz's law. Right. Here, how the current can produce? Current can produce in circular path due to change in magnetic flux. To understand the concept of eddy current, again we will take one more example. How to take one more example? Look at it. So let it this bar magnet. I can take one more example. How the eddy current concept can understand. See. Simply I will take a rectangular coil placed in an uniform magnetic field. Rectangular coil placed in a uniform magnetic field. How it is? See here. I can take simply this is the rectangular coil. This is the rectangular coil. Right. This rectangular coil, like this situation, look at it. This is the rectangular coil I can take. Rectangular coil. This rectangular coil is freely suspended. Look at it. How this is? This rectangular coil, it should be freely suspended like this way. And this rectangular coil is oscillates, freely oscillates. Right. Now this rectangular coil placed in a uniform magnetic field by taking two poles. Shall I take here? Simply I can take this is nothing but one pole. I can call this north pole. Right. What about this? This is south pole. Right around this. Now, magnetic field lines, how they will go? Magnetic field lines can go like this way. Magnetic field lines can travel from north pole to south pole. These are nothing but uniform magnetic field lines. Right. These are uniform magnetic field lines, like this situation. When this coil oscillates, magnetic field lines pass through surface changes. Wherever magnetic flux linked with the coil changes in this coil again, EMF can produce. How the EMF can produce? When coil oscillates, more number of magnetic field lines can change through surface. Consider when this coil is rotating in uniform magnetic field, like this, EMF can induce in this coil. Let us take. These are nothing but EMF induce. You can take direction angle like this also. Let us consider now the current can flow in anti-clockwise direction. When this coil is moving towards the north pole, then EMF induce. How the EMF induce? That EMF induce can flow in anti-clockwise direction. Look at this direction of the current. How this is? When this coil rotates like this, moving like this, oscillates like this, magnetic flux linked with the coil changes and EMF induce in this coil. Right. If the case this coil is nothing but a solid coil. Instead of open coil, it is a solid coil. It is solid coil. When solid coil rotates in uniform magnetic field, how the current can produce? We know that the solid surface in this solid tube or in this solid square, it can take number of rectangular coils. For example, I can take here one rectangular coil. I can take one rectangular coil in this solid. So again I can take one more rectangular coil. Like this rectangular coil I can take. Like this can take number of rectangular coils. Because it is solid coil. In this solid coil I can make the number of pieces. When this coil rotates in this magnetic field, magnetic flux linked with the coil changes at every point. How the current can flow? How the current can flow? Current can flow in this direction. Current can flow in this direction. Current can flow in this direction. This current what we are calling? This current we are calling induced current. Simply I can call induced current. So let it be this coil. Now I can take one more coil here. So one more situation I can take. Again I can take this is magnet. This is magnet. Say north pole I can take. This is south pole. So instead of this coil, simply I can take a solid sphere. Solid sphere I can take. Simply this is a solid sphere. This solid sphere is freely sustained. Here how the eddy current can produce. How the current can produce. We know that magnetic field lines. How the magnetic field lines can travel? These are the given magnetic field lines. They can pass through given surface, perpendicular to surface. These are the given magnetic field lines. These are magnetic field lines. Wherever this solid tube is oscillating this magnetic field, magnetic flux linked with the coil changes. How the current can produce here? How the current can produce? Each electron experience magnetic force in what direction? In this direction, because so many electrons are present. Not only one electron. So second electron, how it is moving? It is moving in like this way, like this way. It is moving in like this way. So that electron moving like this, electron moving like this. What is direction of current here? Direction of current must be this way. This is the direction of the current. I mean, wherever the coil moving or magnetic flux linked with the coil changes, always current flow in a circular path. If the surface is solid, at each part of the solid, the current can flow in a circular path. For example, so I can take it as a solid here, like this solid. Look at me. I can take this is a solid I can take. So I can call this nothing but magnet. This is north pole I can call. This is north pole, this is south pole. How the magnetic field lines can go? These are magnetic field lines. Are you following me? Magnetic field lines. Wherever magnetic flux linked with the coil changes, simply I will do both magnets. Wherever magnetic flux linked with the coil changes, each electron experience magnetic force. How they can move? Actually it is a solid. So due to solid, each electron, how they can move? They can move in circular path. One more electron they can move in circular path, like this way. Like this way, number of electrons, how they can move? They can move in circular path, like this. Right. Because it is a solid. Due to solid, each electron experience magnetic force due to changing in magnetic field. Due to changing in magnetic field, magnetic flux linked with the coil changes. So that how the current can go? Now current can go in this direction, in this direction, in this direction. Or current can go in this direction, like this direction. This direction of the current. Then how the current can produce? The circulating current produced or circulating current induced due to changing in magnetic flux. Simply what I am calling? The circulating current induced in conductor due to changing in magnetic flux. This is called as eddy current. And this eddy current was discovered by Foucault. So this eddy currents are also called as Foucault. See here, eddy currents are discovered by Foucault. They are discovered by Foucault. So this current also called as Foucault current. Foucault current. How the circulating current produce? Question here. Because it is a solid, in solid so many free electrons available. Due to changing in magnetic flux, each electron moving in circular path. Each electron experience magnetic force. Due to that, electrons moving in circular path, so that current can produce in a circular path. Opposite to direction of motion of the electron, the current can produce. Again, the direction of induced EMF is given by here. Simply, I can define eddy current now by taking all these examples. How it is? Wherever magnetic flux linked with the coil changes and circulating current can produce. This is called as eddy current. Look at it here. So, shall I go for the definition of the eddy current? See here. How to go the definition of the eddy current? Look at it. How to write? The circulating current produced or circulating current induced. Circulating current, 'induced' 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 ' circulating current induced due to changing in magnetic flux, due to change in magnetic flux, change in magnetic flux, due to change in magnetic flux, magnetic flux is called as eddy current, is called as eddy current. Is called as eddy current. Simple I can take. See here one more situation I can take. Look at me. So these are the magnets, north pole, and look at me in the south pole. So I can take this is the solid sphere I can take. For my convenience I can take the solid sphere. So in the solid sphere, magnetic field lines can passes. Like this magnetic field lines can passes through the surface. These are the number of magnetic field lines I can passes. Right. How it is? Wherever magnetic flux linked with the called changes, each electron experiences magnetic force in circular path. In this way, all electrons can experience magnetic force. Then how the current can flow? Current can flow like this way. What it is? The circulating current produced due to changing in magnetic flux is called as eddy current. But this eddy current is responsible for large amount of heat. Whatever induced current, that induced current create a large amount of heat due to large amount of circulating current. Wherever currents are flowing in a circular path, large amount of heat can generate it. So one of the disadvantages of the eddy current is it creates the large amount of heat due to changing in magnetic flux. Wherever magnetic flux can changes, large amount of current can produce, along with the heat can dissipated in the form of current. So that due to eddy current, it prevents the insulation between so many parts of the given machine. If a machine is there, when this machine rotates in uniform magnetic field, like you can take AC generator, like you can take the dynamo, wherever dynamo rotates in magnetic field or AC generator rotates, there large amount of heat can generate it. Then question is, what are the uses of the eddy current? Later we will see how the eddy currents can be minimized. See here. Now let us go the uses of the eddy current or applications of eddy currents. Uses of eddy current. See here. Eddy current had lot of uses. Just I will write one by one uses of the eddy current, then I will explain in detail. See here. Eddy currents are used in electromagnetic damping. Electromagnetic damping. Electromagnetic damping. Electromagnetic damping. Next. Eddy currents are used in electromagnetic braking. Electromagnetic braking. Electromagnetic braking. Next one. Eddy currents are used in induction furnace. Eddy currents are used in power meters. They are used in power meters. Fourth one. They are also used in speedometer. So let us explain in detail how eddy currents can use and how eddy currents can minimize. Look at here. Initially, I can take electromagnetic damping. Electromagnetic damping, it stops the vibrating system. It stops the vibrating system. That we are calling electromagnetic damping. How vibrating system can stop? That we will see. See here. Initially I can take a coil. This is nothing but rectangular coil I can take. See here. This is a rectangular coil. This rectangular coil is freely suspended. Look at it. This is a coil. This coil is freely suspended. Are you following me? Now, this coil rotates. This coil rotates in this way. What I say? Electromagnetic damping. It stops the oscillating system. How it stops the oscillating system? Now, it is a freely coil. This freely coil rotates like this. When this freely suspended coil, just I want to put in a strong electromagnet. Say one is north pole, one is north pole, second one is what? Second one is south pole. Then, what are magnetic field lines? Magnetic field lines can travel from north pole to south pole. Like this way, magnetic field lines can pass through a given surface. These are number of magnetic field lines that can pass. When this coil rotates in this magnetic field, I mean when this coil is oscillating in magnetic field, magnetic flux linked with the coil changes. Whenever magnetic flux linked with the coil changes, how the current can induce in this coil? In this coil, current can induce in anti-clockwise direction. Consider like this. Circulating current produce. Circulating current produced due to changing in magnetic flux. This circumpolarity current. Whenever current is flowing in this coil creates its own magnetic field. Here current can flow in anti-clockwise direction. So one end acts as the north, second one acts as the south. Which one is when current can flow in anti-clockwise direction? What about this pole? So this pole acts as the north. What about this pole? This pole acts as the south. Here when this coil oscillates in this direction, so north and north are repel each other. But when this coil comes like this, north and south are attract each other. So how it is? Initially it oscillates like this. When it goes like this, north and north repel each other, it repel like this. When this coil comes in this direction this coil comes. When coil comes in this direction, again this end acts as the south, this end acts as the north. Here attraction takes place. Here repulsion, here attraction. Here again repulsion, here attraction. So that when coil oscillates in this magnetic field, this induced EMF opposes the change in magnetic flux. Due to that, this coil comes to rest. Simply, how to come to rest? When it is oscillating in the magnetic field, due to oscillation, EMF induced in this coil, induced EMF opposes the change in magnetic flux. Due to change in magnetic flux, your north and north repel each other, and it is the south. South and south also repel each other. Here north and north repel each other, south and south repel each other. Due to repulsion, it comes to rest. This is electromagnetic damping. I mean the system which stops the oscillating body. Look at it. Next one, electromagnetic braking. What is electromagnetic braking here? We know that electromagnetic braking, I mean eddy currents are used to control the speed of the electric trains. How it is? Electromagnetic braking mean what? Electromagnetic braking mean the eddy currents are used to control the speed of the electric trains. How it is? To the wheels of the train when magnet is on, circulating current is produced. Due to circulating current, EMF induced. The induced EMF opposes the rotation or the motion of the wheels of the train. So that when magnet is on the wheels of the train, the circulating current produced. The produced circulating current stop the motion of the wheels of the electric train. That we are calling electromagnetic braking. I mean, eddy currents are used to control the speed of the electric trains. Next one. Eddy currents are used in induction furnace. When large amount of magnetic field applied to a circular coil, circulating current produces. Though circulating current causes large amount of heat, it creates large amount of heat. Due to large amount of heat, any material, any conducting material that can melt, so that it is used in an induction furnace. Similarly, eddy currents are also used in electric power meters. How electric power meters is there? Actually, a aluminium aluminium coil or aluminium rectangular coil placed in electric meters. When this magnet is continuously changing, aluminium coil is had to be oscillate. I mean circulating current produce. Wherever circulating current produce, that coil try to rotate in that magnetic field. How much a rotation of that coil, that indicates the amount of power dissipated in electric meters. That we are calling electric power meters. Similarly, eddy currents are also used in speedometers. Speedometer, the device which detects the speed of the vehicle. How it is? A magnet is attached to the axle of the vehicle. When vehicle moving, magnet rotates. I mean magnetic flux linked with the coil changes. Wherever magnetic flux linked with the coil changes, circulating current produces. The circulating current whatever produced, that is nothing but deflection in needle of the speedometer. So that we are calling speedometer. Then due to eddy current, large amount of heat is produced. I mean to avoid the large amount of heat, simply to minimize the eddy current, simply a solid iron core is placed by infinite number of plates. For example, see here, I can take this is a solid body, this is solid body. So due to changing in magnetic flux, I can take it is a north pole. What about this? This is the south pole. Due to changing in magnetic field, how the circulating current can produce? These are the circulating current produce. So it is a solid pipe or solid surface. Due to solid surface, large amount of current can produce. I mean large amount of eddy current can produce. Due to large amount of eddy current, heat also generated in this material. Question is, how to avoid the large amount of heat, or how to minimize the eddy current. Eddy current can be minimized by taking, instead of solid coil, we will take this solid coil with a number of thin plates. See here, how it is? Look at it. When the solid surface makes with a number of thin plates will like this. Shall I take? I can take this is one thin plate. This is one thin plate. This number of thin plates, they can be insulated from each other. So, due to changing in magnetic flux, in one coil current can produce. This second coil current can produce. In this way current can produce. These coils are insulated from each other so that this eddy current only restrict to a one plate, because one coil insulated from another coil, second coil insulated from another coil, so that by taking number of thin plates, due to changing in magnetic field, that circulating current only restricted to a one circular plate or one rectangular plate. Due to that, eddy current can be minimized. How the eddy current can minimize? Eddy current can minimize, instead of a solid body, you can take thin plates which are insulated from each other. Due to that, current can restrict only in a one plate. So these are things that the eddy currents uses along with some disadvantages and how to minimize the eddy current. The remaining concept we will see in the next class. Thank you.